Welcome my dear learners for this course on operations research. In this module 2 we were discussing on linear programming problems. So far we have discussed how to solve linear programming problem using simplex method, big M method and two-phase method. In today's lecture I am introducing you people to the concept of duality in linear programming problem. Duality is an inherent property of a linear programming problem. Any linear programming problem given to us is said to be in its primal form. Let us discuss how to write dual for any given primal. Any given LPP for us is considered to be the primal. For that we should be able to write dual. The advantage is that the solving primal or dual both gives the same optimal solution for the given problem for us. In many a time solving dual is more easier compared to the primal problem which is thrown to us. So therefore learning how to write dual for any primal gives us an advantage that solving dual will become much more easier. However, the solution of both primal as well as dual is same. Now in order to discuss what is duality in linear programming problem, let us consider the problem number 1, which states that zmax is equal to 6x1 plus 5x2 subjected to x1 plus x2 less than or equal to 5, 3x1 plus 2x2 less than or equal to 12, x1 and x2 are positive variables. Now our aim is to find out what is the maximum value of z that this linear programming problem can accompany, such that it should satisfy these two constraints. We have two constraints, two variables and one objective function. Our aim is to determine what is the maximum value of z. Now simply saying the upper bound, the highest value of z that the linear programming can accompany is infinity. Right? Beyond infinity there is no number, so therefore z max can be infinity is the first wild guess. Right? So first wild guess is that z max can become infinity. So this is the upper bound. Our aim is to determine what is the exact value of z max. What is the maximum value of z max, numerical value of z max that this problem can accompany. Right? So now one more thing, if you carefully observe, if I multiply equation 2, consider equation 2, 3x1 plus 2x2 is less than or equal to 12. Multiply equation 2 with 3. So multiply equation 2 with 3. So I will get the second upper bound for this problem, that is if I multiply it with 3, I will get 9x1 plus 6x2 should be less than or equal to 36. Right? So this 9x1 plus 6x2 is greater than 6x1 plus 5x2, you will agree. So therefore the maximum value of z should be less than 36. So therefore I would say that the upper bound for the problem might be 36. So I improved from infinity to 36. Now again one more way to determine the value of z max is that I have x1 plus x2 less than or equal to 5. Multiply this equation by 6. So multiplying first equation by 6 will give us 6x1 plus 6x2 less than or equal to 30. So therefore I would say that z max upper bound will be 30. We have improved from 36 to 30. Now one more thing is that I will multiply equation 2 by 2 and equation 1 I will add to that. So if I do that, what I am doing, equation 2 I will multiply by 2 plus equation 1 into 1. So that will gives us 3 to the 6 plus 1 7, 7x1 plus 3 to the 6 plus 2, right, 2 to the 4 plus 1 5, 5x2 should be less than or equal to 12 to the 24, 24 plus 5 is 29. Now 7x1 plus 5x2 is less than or equal to 6x1 plus 5x2, correct? So therefore the upper bound for this problem is 29. Z max cannot exceed 29. Is it optimal solution? I don't know. It is a wild guess, right? From infinity I keep on improving the value of z max. So therefore I found that the upper bound for z max is 29. Is it optimum? I don't know. I should solve this linear programming problem and find out whether the answer is 29 or not. But through the rough estimate I found out that I got Z max upper bound as 29. So I can clearly state that this problem has the value of Z max which is less than 29. Now, in the similar approach, if I multiply equation 1 by some variable a1 and equation 2 by some variable a2 such that 1a1 plus 3a2 is greater than 6 and 1a1 plus 2a2 is greater than 5, then obviously 5a1 plus 12a2 will be the upper bound for this problem. So I will multiply this equation by a1, this equation by a2, and vertically I will take that a1 plus 3a2 is greater than 6, a1 plus 2a2 is greater than 5, then obviously 5a1 plus 12a2 will be the upper bound for this given linear programming problem, which will gives us one more linear programming problem, which is nothing but dual. What I mean to say is that multiply this by a1, this by a2, and vertically you take the constraints. That is, I multiply equation 1 by a1 and take it as a1. So we have, and this by a2, vertically I will take it as a1 plus 3a2 should be greater than or equal to 6. So this I multiplied by a1, this I multiplied by a2, so 2a2, and the constraint is that these should be greater than 5. Then I will get the upper bound as 5a1 plus 12a2. 5a1 plus 12a2 will be the upper bound, is the upper bound for this problem, provided a1 and a2 are positive values. This gives us one more linear programming problem which was derived from the original primal. So this is the dual for the given primal. Here the objective function is that I should find a minimum value of the upper bound. What I am doing, I am estimating the minimum value of the upper bound. So therefore here the objective function is changed to, I want to find the minimum value of z, which is the upper bound for the original problem. So therefore every given problem will have dual inherent in it. So the dual for the given primal problem can be written very easily once it is in its standard form. The standard form of a primal is standard primal. A standard primal will have objective function is to maximize, objective function is to maximize, and constraints are of type less than or equal to, always. If the objective function of the given linear programming problem is to maximize and all the constraints have less than or equal to sign, then such given linear programming problem is said to be in its standard primal form. So therefore the given problem is in its standard primal form. So therefore primal of the given problem is what we have, z max is equal to 6x1 plus 5x2, subjected to the condition x1 plus x2 is less than or equal to 5, 3x1 plus 2x2 is less than or equal to 12, and x1 and x2 are positive values. So whenever we have a standard primal, objective function is to maximize and constraints have less than or equal to sign, such primal can be easily, such dual for such primals can be easily written. That is, the objective function will become right hand side of the constraints and the right hand side of the constraints will become the objective function, and the coefficient of the constraints will become transpose. This is the condition for writing the duality. So therefore the dual for this primal will be, the objective function of the primal is maximization, so therefore objective function of the dual will be minimization. The RHS of the constraint will become the objective function, hence it is 5y1 plus 12y2. Now objective function of the primal will become the RHS of the constraints in the dual. So therefore the constraints should be 6 and 5. So the values of the coefficients of the constraints should be transposed in dual. So we have 1x1, so that is 1 by 1. Here we have 3x1, so therefore it is plus 3 by 2. Here we have constraint less than or equal to, so therefore this should become greater than or equal to. Here also you transpose it, so it will be y1 plus 2y2 greater than or equal to 5. y1 and y2 are positive values. So this is how you should write dual of any given primal. You have learnt how to write dual for a primal when the primal is in its standard form. What is the meaning of standard form? The objective function of the primal should be always maximization. If given as minimization, multiply this by negative sign throughout, you will get the maximization. And the constraint should be always less than or equal to. Then only you know how to write the dual. So therefore, if any given problem is not in its standard form, first try to get the standard form of the primal. Then for that primal, write the dual. Then satisfy the properties. The properties are the number of constraints in primal will become the number of variables in dual. The number of variables in primal will become the number of constraints in dual. This is very, very important. In a given primal, the number of constraints will become the number of variables y1 and y2. The number of variables x1 and x2 will become the number of constraints. So since we have two constraints with two variables, we cannot differentiate here properly. Let me address problem number 2, which gives us more clear picture how to write the dual for a given primal. So hope you understood. The properties are very, very important to write the dual for any given primal. Now with this very brief knowledge on duality of any given linear programming problem, let us address problem number 2, which involves all varieties of constraints. We have equation, we have greater than or equal to sign, we have less than or equal to sign, we have unrestricted variable. So if you learn how to write the dual for this problem number 2, you can write for any given primal problem, you can write dual. So come, let us address problem number 2. Now moving ahead for problem number 2, we have the given linear programming problem, that is primal has z minimum is equal to 8x1 plus 5x2 plus 4x3 subjected to the constraints 4x1 plus 2x2 plus 8x3 is equal to 12, 7x1 plus 5x2 plus 6x3 greater than or equal to 9, and 8x1 plus 5x2 plus 4x3 less than or equal to 10, and 3x1 plus 7x2 plus 9x3 greater than or equal to 7. Coming for the variables, x1 is greater than or equal to 0, x2 is unrestricted, and x3 is less than or equal to 0. Now if you carefully observe, the given primal is not in its standard form. First I should convert the given primal into its standard form. For the standard form, we have learned how to write the dual. So therefore, in step 1, you convert the given primal to its standard form. That is, the objective function of the primal should be maximization, and all the constraints should have less than or equal to sign, and all the variables should be positive. Now if I do that, if I go for the solution of problem number 2, first convert the given primal to its standard form. We have the standard primal as z max is equal to minus 8x1 minus 5x2 minus 4x3. So this is subjected to the constraints 4. So we have the equation converted into constraint. So this equation can be written as two constraints as 4x1 plus 2x2 plus 8x3 less than or equal to 12 is 1. Second one is 4x1 plus 2x2 plus 8x3 greater than or equal to 12. I have converted this equation into its constraint form. Now here we have greater than or equal to sign, which is undesirable for a maximization objective function. Hence throughout multiply this by negative sign. If I throw multiply this by negative sign, I will get the constraint as minus 7x1 minus 5x2 minus 6x3, which is less than or equal to minus 9, which is desirable. Now here we have less than or equal to sign, no need to worry, write it as it is 8x1 plus 5x2 plus 4x3 less than or equal to plus 10. Again here we have greater than or equal to sign, so multiply throughout by negative sign, which gives us minus 3x1 minus 7x2 minus 9x3 less than or equal to minus 7. Now we have x1 which is positive, x2 is unrestricted, and x3 is negative. But I want all the variables to be positive, so therefore convert this into positive variables. That is, let us write x2 as x4 minus x5. Since x3 is negative, let us write x3 as minus x6 minus x6. So where we have x4 and x5 are positive, and also x6 is positive. So since x6 is positive, multiplying with negative sign, I will get x3 as negative, which satisfies the given condition. Hence, we will get the standard primal as, we will have the standard primal as Z max is equal to minus 8x1 minus 5x4 plus 5x5 plus 4x6. Correct? I replace x2 by x4 minus x5 and x3 by minus x6. So this is subjected to the constraint. We have 4x1 plus 2x4 minus 2x5 and minus 8x6, which is less than or equal to 12. So since we have greater than or equal to sign, convert this into less than or equal to by throughout multiplying with negative sign. So hence I will get minus 4x1 minus 2x4 plus 2x5, minus of minus will become plus 8x6 less than or equal to minus 12. So remaining 3 have less than or equal to sign, no need to worry, just replace these things. That is minus 7x1 minus 7x1 minus 5x4 plus 5x5, minus of minus is plus 6x6 is less than or equal to minus 9. Next we have 8x1 plus 5x4 minus 5x5 minus 4x6, which is less than or equal to plus 10. Last constraint is minus 3x1 minus 7x4 plus 7x5 plus 9x6 is less than or equal to minus 7. So now we have x1, x4, x5, x6 are all positive variables. So this is the required standard primal. That is, the objective function is to maximize, the constraints are less than or equal to sign, and the variables are positive. Now for this standard primal, write the standard dual. dual for the standard primal. We don't have standard dual, so dual for the standard primal. Dual for the standard primal. So this is the standard primal for which you write dual. The objective function is to maximize, so therefore here the objective function will become minimization. The objective function should become right hand side of the constraint, and right hand side of the constraint should become objective function. So therefore the objective function will be plus 12 y1 minus 12 y2 minus 9 y3 plus 10 y4 minus 7 y5. Now the objective function will become right hand side, so the right hand side should be minus 8 minus 5 plus 5 and plus 4. So this should be transposed. So if I transpose this, I will get 4y1 minus 4y2 minus 7y3 plus 8y4 minus 3y5. This should be greater than or equal to minus 8 because we have less than or equal to sign here. Next you transpose this one. If I transpose that, I get 2y1 minus 2y2 minus 5y3 plus 5y4 minus 7y5 greater than or equal to minus 5. Next coming here, we have minus 2y1 plus 2y2 plus 5y3 minus 5y4 plus 7y5 greater than or equal to plus 5. And coming for the last one, we have minus 8y1 plus 8y2 plus 6y3 minus 4y4 and plus 9y5 greater than or equal to 4. Now all these variables y1 to y5, y1, y2, y3, y4 and y5 are all positive variables. So this is the dual for the standard primal. But our aim in this problem is not to find the dual for the standard primal. Our aim is to find the dual for the given LPP, that is for the given primal. Now convert this dual to the dual of the given primal. This is a dual for the standard primal, but I want a dual for the given primal. Now converting this to the dual of given primal, that is dual of given primal. Now to convert this to dual of given primal, the objective function of the given primal is minimization. So therefore objective function of the dual for the given primal should become maximization. So here I should get maximization. Hence throughout I should multiply by negative sign. So therefore throughout you multiply by negative sign, you get minus 12y1 plus 12y2 plus 9y3 minus 10y4 plus 7y5. Now here the RHS should be positive because we have the objective function as plus 8, plus 5 and plus 4. Here I have minus 8, minus 5, 5 and 4. So here I have plus 4, no need to worry. But here I have 4 constraints, but here I have only 3 variables. We know that the number of variables in the primal should be equal to the number of constraints in the dual. So since I have only 3 variables x1, x2, x3, here I should get only 3 constraints. But I have 4 constraints here, which means that I should club these 2. I can club these 2 if I multiply the second one throughout by negative sign, or if I multiply the first one throughout by negative sign, I can convert these two can be clubbed, right? So let us club these two by multiplying this by negative sign. Multiply this by negative sign. The second equation is multiplied by negative sign. If I multiply this by negative sign, these two can be clubbed and written as an equation. And this I multiply by negative because I want plus 8 in the RHS, because I have RHS is plus 8, plus 5 and plus 4. So therefore the second equation I will multiply by negative, and the first equation also I will multiply by negative. So if I do that, I will get the constraint as subjected to the constraints. So this is constraints. Subjected to the constraints minus 4y1 plus 4y2 plus 7y3 minus 8y4 plus 3y5 is less than or equal to plus 8. Now if I multiply throughout by negative, this will become less than or equal to, one has greater than or equal to, one has less than or equal to, and both the equations are similar, so therefore I can club these two. If I club these two, I will get minus 2y1 plus 2y2 plus 5y3 minus 5y4 plus 7y5 is equal to plus 5. So I multiplied this by negative sign. These two equations are similar. One is less than or equal to, another one is greater than or equal to. So I clubbed these two. So if I multiply this throughout by negative sign and observe, these two will become similar. One with less than or equal to sign, one with greater than or equal to sign, which means there is an equation. I clubbed it and formed an equation. The last one, I will write it as it is, minus 8y1 plus 8y2 plus 6y3 minus 4y4 plus 9y5 is greater than or equal to 4. Done. Now for this problem we have y1, y2, y3, y4 and y5 are all positive variables. Now again compare the property. We have the objective function should become the RHS 854. We have 854. The RHS of the constraint should become the objective function, which is 12, 9, 10, 7. But we have two 12s, so therefore I should club these two. So club these two. And we have plus 9, we have plus 10, but here I have minus 10. So I'll write it as, let y6 is equal to y2 minus y1. So where y6 will become unrestricted, and y4 I'll write it as minus y7, where y7 is negative. So negative of negative will become positive. So if I replace, I will get plus 10 here. So hence the required dual will be, hence the required dual for the given primal will be Z max, which is equal to 12 by 6 plus 9 by 3 plus 10 by 7 plus 7 by 5. So y2 minus y1 is y6. Hence the constraint will be subjected to the constraints 4 by 6 plus 7 by 3 plus 8 by 7 plus 3 by 5, which is less than or equal to 8. Here I will get 2 by 6 plus 5 by 3 plus 5 by 7 plus 7 by 5 is equal to 5, and finally we have 8 by 6 plus 6 by 3 plus 4y7 plus 9y5, which is greater than or equal to plus 4, which is greater than or equal to plus 4. So where we have the constraints as y6 has become unrestricted, y3 and y5 are positive, whereas y7 is negative. Now we compare the dual with the given primal. The operative function of the primal has become the RHS of the dual 8, 5, 4. The right hand side of the constraints of the primal have become the operative function for the dual 12, 9, 10 and 7. The number of constraints are 4, hence the number of variables are 4. And the number of variables are 3 in the primal, hence the number of constraints are 3 in the dual. Correct. One more point I should make here is that if you carefully observe, the first constraint is equation, hence in the dual the first variable is unrestricted. Here the second variable is unrestricted, hence the second constraint is an equation. So therefore equation will become unrestricted variable will become equation in case of primal and dual relationship. So this is how you should write dual for any given primal, that is write this standard primal for the given primal. So once you write the standard primal, you know how to write the dual for the standard primal. Written. Now using the properties of dual and primal, try to get the dual for the required primal. So this is a dual for the given linear programming problem. Any linear programming problem given for us is in its primal form. Now we have seen that the dual is inherent in the primal. Now it is easy for us to solve this one compared to. So in our next lecture, let us discuss